So if you don't have, let me ask you questions. So what is this? I said this corresponds to some theorem in algebra. So what was this right-hand side? What is the theorem it corresponds to? Can somebody please mention that theorem? The theorem in algebra that this one corresponds to. Corresponds in a loose sense, but we did this last time. No?
Chinese remainder theorem.
Right. Chinese remainder theorem. Very good. So the idea here is, let's recall. So you take, so let me do it in the following. Let me call it A of t be any polynomial in K of t. Remember, K is a field and T is a variable, such that A of t is 0. So what do I mean by this? So T is a linear, recall T to V, from V to V is a linear transformation, K linear transformation. Map, K is a field, fixed, and V is a finite dimensional vector space, fixed. It's a finite dimensional K vector space. And we make this V into a KT module by T. So V becomes a KT module. By T acting as. Okay. Okay, so this makes sense. AT is 0. So if I plug in capital T for T, then I get 0. Let AT, let the, so A1 to the R1T, AK to the RKT be the decomposition into okay. So let me say it with A1 AIT not equal to AJT or I not equal to J. And A1T AKT irreducible. Then, okay, here is the statement. V is the kernel of A1T to the R1, direct sum kernel of A2 R2T, direct sum kernel of A K. Oh, we can, okay. So instead of this T, you can write a capital T. It doesn't matter which T you write. You can write either T, but just since I wrote a capital T here, I am writing capital T here. So let me write this clearly. This is this. Okay, and the idea is that this V is actually, because this AT is 0, what this means is the kernel of A of T. So this is actually the kernel of A of T. because AT0 means the operator, it acts as a zero operator, which means the kernel of AT is the zero operator. The kernel of zero operator is the whole space. So this is actually the kernel of AT, and that's equal to this. This is the primary decomposition. So in particular, you can apply this too. So we can take A T to be the minimal polynomial. And AT equal to 0 in that case by definition, because by definition, the minimal polynomial is a polynomial that is satisfied by T, of T, of course. Everything is of T. We can take AT to be the characteristic polynomial of T as well, because that too satisfies T. I mean, T satisfies the characteristic polynomial. This is by the Cayley-Hamilton. Okay, so you can apply it in these cases. Okay, and as we were, so let me remind you, so if you take, if K is algebraically closed, right? For example, if it is C, then the irreducibles, then AIT is equal to T minus lambda I. Right? Each one of them, the only irreducibles over an algebraically closed field are linear polynomials. Okay, so what we get is that, and we get V is equal to kernel of A. This one will be T minus lambda 1 with the R1 direct sum kernel of T minus lambda K RK. Okay. One more parenthesis if you want here. Okay, and as we said last time, this is called the generalized eigenspace. Generalized lambda 1 eigenspace. And this is the, so this whole thing is the generalized lambda K eigenspace. And let me also remind you, so dimension of this thing, T minus lambda I to the Ri, this is called algebraic multiplicity. This is the definition of algebraic multiplicity. Of the pair of lambda I with respect to T, if you wish. Maybe you can use a slightly different language here, but I hope you understand. And there is also a dimension of kernel of T minus lambda I, which, as we know, this is the geometry, this is the eigenspace. This is the lambda eigenspace. This is the geometric multiplicity. Okay, and so since so assuming Ri are bigger than or equal to Ri bigger than or equal to 1, we have dimension of this, sorry, even the kernel T minus lambda I to the Ri. This is a bigger space than this. anything that is killed by lambda, t minus lambda is going to surely be killed by some higher power. So naturally, this dimension is going to be bigger than this, which means this algebraic multiplicity is bigger than or equal to this geometric multiplicity. Okay. Any questions on this? Okay. As so last time I made some general comments about how this is related to the Chinese remainder theorem. But in any case, so a formal proof, for a formal proof, of this primary decomposition theorem will be explained or will be done in the tutorial sheet that I'm going to distribute right after this lecture. Okay. I may add more problems later on, but I'll share the tutorial sheet as it is right now. In fact, I can do that on the chat. Oh, but I can't send a PDF file on chat, right? I can't do that. Okay, never mind. I'll send it at the end of the lecture. Okay. So let us start talking about the Jordan canonical form. So I'm sure you've seen this. Can somebody say what the point of Jordan canonical form is? I think I explained some of it in the beginning of lecture 2, I think. But can somebody recall what the idea of Jordan canonical forms? I'd explained what form means, etc. So what is the idea here? You will have to help me because you know, without some response from you, I'm totally lost. I don't know whether what I'm saying is making sense or not. I need some feedback. So I hope, I request some of you to respond, even if it is only to ask me to explain it once more.
We define an equivalence relation on a set of all linear transformation.
Say that again, ma'am. I couldn't quite hear you.
We define an equivalence relation on the set of all linear transformation.
Yeah, very good. Yes, very good.
And to identify the unique representation of the equivalence class, we need Jordan canonical form.
Very good. Excellent. Okay, very good. Right. Indeed, that's correct. So this gives a unique representative. So this gives unique representative in each equivalence similarity class. So the equivalence relation that you put on linear transformations is if two transformations are similar in each similarity class of matrices or transformations of matrices, by which we mean n cross n matrices or d cross d matrices, because our notation is that dimension B is D of matrices, or linear transformations. Okay, very good. That's indeed correct. Very good. So I assume everybody understands that. So let me not belabor that point. If that needs to be explained, please, this is your chance. Please do ask. Otherwise, I'll assume that this is something you understand very well, and I will proceed.
So could you please explain again?
Okay. So sure. Thank you. Thank you for that. So this is a picture I like to draw. I'm very fond of. So let me draw that again. I drew this the previous time. So imagine this is a schematic picture. So you should not take this too literally. So this is the set of all. Let's do it in terms of matrices. Set of all D cross D matrices. Okay. And I put the equivalence relation. Suppose A is a matrix in here, D cross D, and B is another matrix. I say A is equivalent to B if there exists an invertible D cross D matrix G such that I call it small g because it's an invertible matrix. So I'm thinking of it like a group element or something, right? It said the set of invertible matrices form a group under matrix multiplication. So G inverse is equal to B. So this is just matrix multiplication. G is also a D by D matrix and it's invertible. So G inverse is a D by D matrix. So G inverse is equal to B. Okay. So this is an equivalence relation. If A is equivalent to itself, if A is equivalent to B, then B is equivalent to A. And if A is equivalent to B and B is equivalent to C, then A is equivalent to C. So this is an equivalence relation. And once on any set, if you have an equivalence relation, the equivalence classes form a partition, right? So let's say the partition looks something like this. This is again very schematic. Okay. So these are the equivalence classes. Right? I mean, there could be, this looks like a finite picture, but there could be infinitely many equivalence classes. Of course, nothing stopping there. In fact, in this case, there will be infinitely many equivalence classes. Okay. Now, what we want to do in a situation like this, it's a very natural question to ask, look, can I just choose one element here from each of these classes? So I'm also fond of this analogy. Some of you may have heard me saying this, so please bear with me if you have heard this before. But a good example to keep in mind is constituencies, say in an election. Okay, so they say this is the map of, Uttar Pradesh elections are going on. So this is the map of Uttar Pradesh, say, and this is the constituencies, right? So in fact, this approximately looks like Uttar Pradesh, its shape. Okay, and what are we going to do in an election? We are going to elect one person to represent each constituency. So in each constituency or in each equivalence class, there is one person that is going to be identified, and we are going to say that that person is our representative, right? So similarly here, the Jordan canonical form is one of these special matrices. So this person going to be elected is a special person, right? The MLA, right? So you can say that he is the Jordan canonical form. If the constituency is the similarity class, then the MLA is the Jordan canonical form. That's one, one analogy. I hope that helps you understand the concept better. Okay, so this is a very special matrix, right? And there is only one in every similarity class. Okay. So does this make it better? So not only with, yes.
Clear,
Yes.
but I have two doubts.
Yeah,
Maybe
please,
highly.
please. No, even if
don't
it is
think that
please feel free to ask doubts. Doesn't matter if it is if you're not sure whether it makes sense or not. Please, yeah, please ask.
Maybe it may be it may be very premature to ask this doubt now, but let me clear two things about Jordan canonical form. One thing is you are saying that it's a representative of each equivalence class. What does it mean, the representative? How what is the word meaning of that representative? First one.
Okay.
Second doubt is normally linear algebra is motivated by solving a system of homogeneous linear equations. That's the motivation of linear algebra. How far this Jordan canonical form is being connected with the sense of solving a system of equations?
Okay, good question. Okay, so representative. Okay, let me answer your first question. So the representative just means it belongs to that equivalence class. That's all.
Then each member can be considered as a representative.
Yeah, you can choose some other representative from that class, right? But what we want to do is, see, you want to say that if you see, if I see, the idea is that you will define a certain pattern, right, or a form, that's right, and you say I will in a matrix of this form, there is exactly one in every similarity class. So it is in some, so on the one hand, I said representative could be any element belonging to this similarity class, right? Anybody, any other element here would also be a representative, all right? But see, I mean that, there is, that is sort of not so useful. If I say, okay, from each one, I pick one, right? The question is, how do I pick one, right? There are infinitely many classes in this case, and what you want to do is, or even if there are finitely many, what you want to do is pick something of a fixed pattern, fix a pattern, and then of that pattern, there is exactly one you want to select. Does that make sense?
Can I understand like this, that the Jordan canonical form is the matrix that will give the total information of the corresponding equivalence class, or can be considered as a dimension of a vector space?
Well, it will give you information about that equivalence class. That's correct. But see, any other matrix will also do that in that equivalence class. Right? If two matrices are similar, as long as I pick a similar, see, what I'm trying to say is, okay, so let me give you another example. So you know row reduced echelon form, right? Correct? Do you, can I assume that you know that? I mean, do you recall that? The concept of row reduced echelon form, or REF. See, there again, what you're saying is you're picking one element from every equivalence class. The equivalence class there is the matrices, belonging to a subspace, right? Of all the matrices belonging to a, I don't know, let me. Okay, with all the, so, okay, you call two matrices equivalent there if they have the same row space. Okay, if two matrices have the same row space, or in other words, if you can go from one to the other by doing elementary row operations, which means the same thing, then they are said to be equivalent. And the row reduced echelon form, what you're going to say is, okay, if I'm going to look at a matrix with certain properties, it must have the first non-zero entry in every row must be 1, etc., etc. There are some properties. Let's not go through the entire set of properties, but you're going to say, I'm going to impose these properties. And once you impose these properties, it turns out there is exactly 1 in every equivalence class. So the idea is that it is not that you are choosing arbitrarily something here. The theorem is saying that of this pattern, there is exactly 1. Does that make sense?
Okay, Professor, I think I have to study more. Thank you.
Okay. So you see, the point is, you want to pick 1 from every class. Correct. Representative just means that there is 1 in every class, nothing more. But how do I pick that representative? You should have an efficient way of picking that representative, right? In other words, you should have a, let us call it an election procedure. An election procedure is one which picks from each class exactly 1 matrix, right? So there could be several procedures. You could say, look, I go into every similarity class and pick 1 randomly, right? But that's hardly, that doesn't give you any insight. But so the Jordan canonical form is actually a procedure. It's at the end of which you will get exactly one matrix in every class, right? So, okay, I hope it will be clear when we actually state the theorem. Okay. And as to your second question, linear algebra is about understanding, you said homogeneous linear equations. It's not just about homogeneous linear equations. Linear algebra is about study of linear equations, period. Whether they are homogeneous or inhomogeneous doesn't matter. Okay, it is the study of linear equations. But what you realize really is that in order to completely understand this structure, you really need to know what the structure of a linear transformation is, right? And once you come down to that, then this Jordan canonical form is telling you that there are exactly these many linear transformations. Because see, any matrix here as a linear transformation, it's the same as something else. They are all similar. So I'm not able to explain this very well at this point, but what you said is correct. Linear algebra is about the structure of study of solutions to linear equations, whether homogeneous or inhomogeneous. Okay, but then from there, what you realize, in order to understand that, you really need to also understand the structure of a linear transformation. Okay, and that the Jordan canonical form helps you to do. This, of course, only if the field is algebraically closed. Okay, so I'm afraid I have not maybe explained it very well, but nevertheless, let me ask if there are other questions. Thank you for those questions.
Thank you, Professor.
Okay, so this is we need to assume K is algebraically closed. So I'll state the theorem, and then hopefully the meaning will be clear. So what we want is a procedure that tells me that of this pattern, there is exactly 1. Okay, and here is the statement. So a matrix let me call it, okay. A Jordan block. Okay. A Jordan block, let's call it a Jordan block, is any matrix, any square matrix of the following form. So you have this is a square matrix. Let's say D by D matrix. Maybe I'll make it C by C matrix. C by C matrix. There are lambda, lambda, lambda on the diagonal. Same scalar, which could be 0, possibly, or some other non-zero scalar. And all the things above the diagonal are that. The rest are all 0. Okay, by these big zeros, I mean all other entries are 0. So the thing is, so let me write it out in words. The diagonal entries are all equal to the same scalar. That's one thing. And then what should we call it? Entries, all entries just above the diagonal are 1. If a matrix is of this form, then you call it a Jordan block. Okay, and then when do we? So what's a Jordan form? Okay, so a matrix is said to be in Jordan form if it looks like the following. So you have a big matrix. Now let's call it D by D, and it is made up of smaller matrices. So something like this. Okay, these are all 0. These are all 0. And what you have here is J1, J2, etc. J, let me call it, with J1, J2, Jk being Jordan blocks. Of possibly varying sizes. Okay, let's do some examples. Okay, so an example would be, so let's look at, so okay, these are examples of, so let's put that in different color. Examples of matrices in Jordan. Okay, so if I have a diagonal matrix, so let's say lambda 1, lambda 2, lambda 3, and so on. So this is a diagonal matrix. Then it is in Jordan form, because you can take the Jordan blocks to be just this 1 cross 1. So each thing is so it follows this definition, because here in this Jordan block definition, it could be a 1 cross 1 matrix with just a lambda there. Okay, and and also here and various lambda. Okay, so there the lambdas could be different. The lambda for this, lambda meaning the diagonal entry for this block, could be different from the diagonal entry for this plot, could be different. They could be the same, no problem. And their sizes could also vary. Here, they are all of size 1 cross 1. Okay, let's do another example. So here, for example, so if I have a matrix like this, right, this is in Jordan form because here, this is it. This is one Jordan block. This is the other Jordan block. Okay. Okay, let's do one more example, maybe, or a few more. So here, let me put 2, 2, 1, 3, 2, 2, 2, 1, 1, something like this. Okay, all the other entries are 0 here. And then 0, 0, 0, 0, 0, 0. Yeah, something like this. Now this is in Jordan form because here this is this block, right? And then there is this block, and then there is this block. Okay, it's okay that these two is the same as this two. We don't care, right? They are possibly varying lambdas, but they could be the same. The sizes could vary, the lambdas could vary, they could be the same, the sizes could be the same. As long as these are Jordan blocks, they're okay. Okay. One thing to keep in mind here is that we do not, so we if two matrices are in Jordan form, and if I permute these, we consider them to be the same. Okay, so let's make that definition. So given a matrix J1, J2, Jk in Jordan form, where J1, Jk are the Jordan blocks, let me not even say the Jordan blocks. Let me see if I can say, yeah, let me say the Jordan blocks. Then it is considered the same as if I permute the blocks. If I take this and put Ji1, Ji2, Jik. That is, if I, instead of, let's say there are 3 of them, J1, J2, J3, instead of taking that order, I put J3, J2, J1, right? Something like that. So, where I1, I2, Ik is any permutation of I1, I2, okay. Right. So then here is now the theorem. Now see, the thing is, what is so special about Jordan canonical form? We have said that we have now defined what it means for a matrix to be in Jordan form, right? It must consist of Jordan blocks. That is one. And we've seen what a Jordan block looks like. It looks like this lambda, lambda, lambda on the diagonal and 1, 1, 1 on top, right? And moreover, two matrices in Jordan form are supposed to be considered the same if I have just permuted the blocks. Right? If they are the same blocks in some order, you could write them in one order, I could write them in another order. Then we consider the matrices to be the same. And then the theorem is And this is the election procedure. So this is what makes it interesting, right? So if I put this condition, that a matrix is in Jordan form, right, then there is precisely one matrix in every equivalence class. Of course, when I say precisely one matrix, I am considering permutations of the Jordan blocks to be the same matrix. So the theorem is there is precisely one and only one. So let me put that, meaning one and only one. That's what it means. There is precisely one matrix in Jordan form in each equivalence class, in each similarity class. Similarity class of D by D matrices. So this should answer the question about representative, the meaning of word representative. So by representative, of course, we mean that from each one I pick precisely one and I call it the representative, right? That is the definition. If that is the case, we call that a representative of that equivalence class. That's correct. But then we are saying something more here. See, we are, of course, you could say, I take this equivalence class, pick one person. I take this equivalence class, pick one random person, right? That would be like just going to every constituency and picking one random person from the constituency and imagine a legislative assembly consisting of these people picked at random, okay? On the other hand, what we are doing is we are doing something, I mean, of course, that would be easy to do, but not very meaningful, right? So what we are doing is we are running an election, right? And we are trying to pick a person whom most of us will vote for, right? Anyway, let us not take this analogy too far because at some point it will break. It's only an analogy. The point here is that it's this. I have put this relatively very simple condition, namely the matrix should be in Jordan form. And once I insist that it be in Jordan form, there is precisely one matrix in every similarity class. That is the beauty. So if you can find a condition of this nature, right, that will identify, that will have this property. There is precisely one matrix satisfying this condition in every class. Then you are in business. Then you have a theorem. So the row reduced echelon form also has this property. So there is a unique matrix in row reduced echelon form which is in every row equivalence class of matrices. Okay, similarly, there is exactly one matrix in Jordan form in each similarity class. Okay, so this is when we do a thing like that, this is like a kind of what you call a classification theorem or a structure theorem, or these are very powerful because basically you can say, suppose I take a linear transformation which is equivalent to a matrix, and then I say I'll just take that matrix to be in Jordan form, right? So I can do that. Okay, so okay, let me again ask if there are any questions, even if I have not explained my response to the earlier questions were not adequate, perhaps.
Sir, I have one doubt.
Sure.
So in this representation, if we can we take one below these diagonal entries, lambda?
Absolutely, you can do that. That would be also, suppose I define these ones instead of a Jordan block to be having ones on top of the diagonal, you could take them below the diagonal. That would also be all right. Okay? But you can't do both at the same time.
Okay, sir.
You have to do one or the other. You understand that, right? In fact, some books may even define it that the other way. Okay, yeah.
Okay,
As long it's like choosing one convention and sticking to it, right? If you choose the upper ones, then this theorem is true. If you choose the lower ones, then the theorem is true, right? But you should not allow both. Okay.
Okay, sir.
Yeah, very good. Thank you. That's a good question. Yeah. Any other questions? So let me ask you a question. So given a matrix, square matrix, so and let's say we are over an algebraically closed to. So let's just take it to be over complex numbers. So I ask you whether it is always similar to an upper triangular matrix. What will be your answer?
Yes, sir. Because in complex we can factorize each polynomial, like then we factorize, so we can represent each diagonal value in some. So because these represent eigenvalues lambdas.
Yeah. They are eigenvalues, correct? So yes. So the matrix. I mean, any polynomial will factorize into linear factors. That's correct. Yeah, that's correct. From there, yes. The answer is yes. Yeah. But how do you know how to prove that? Off the top of your head, how would you prove that?
No, proof is not.
Well, it's not so hard to prove, but the point is, the answer is yes, because look at the Jordan form. It's an upper triangular matrix, right? If I know the Jordan form, if I know this theorem, it contains as a special case that theorem. That's the point I was trying to make, right? Because every matrix is similar to a matrix in Jordan form. And the way we have defined the Jordan form here, it's an upper triangular matrix in particular. In fact, it's an upper triangular matrix of very, very special shape. Right? In particular, it's an upper triangular matrix. Okay. So this theorem contains that theorem that you can every matrix is over complex numbers, every square matrix is similar to an upper triangular matrix. Okay. So that statement is a very special case of this theorem. Okay, so now I want to now talk about the proof of this theorem. How would you go about proving this? Any ideas? So remember, in a general thing in mathematics is this looks pretty hard to prove this, looks complicated at least, if not hard. Is to look at special cases. So are there special cases in which I can prove this thing? That's the question to ask. Or can I prove, for example, can I prove, okay, maybe I for a start, can I prove that it is similar to an upper triangular matrix, for example, or matrices in which in these, maybe they are not in Jordan blocks, but I have lambda. Maybe it's difficult for me to get 1, 1, 1, 1 on top of the diagonal, but at least I have lambda on the, 1, 1, 1, 1 on top of the diagonal, but at least I have lambda on the diagonal. So if I do not insist on this 1, 1, 1, 1, 1 to begin with, but only the lambda on the diagonal, can I get it? Can I write a matrix of that form to which my any given matrix is similar? Right? Okay. So the idea here is, are there special cases in which I can prove this here? How can I reduce it? That's the question. Okay. So when we think of these proofs, I'm afraid, the general tendency is to just, sort of look through pick up some book, look through the proof, and if I, for lack of a better word, I'll say memorize the proof, right? But I would suggest sort of analyzing the proof, stepping back, thinking about it, and breaking it up into pieces and trying to understand it piece by piece, right? Piecemeal. So that would be a good strategy. So with that in mind, how would we go about this? Well, one thing was, for starters, we have this how to say, primary decomposition theory. So this, of course, comes with the assumption that K is algebraically closed. I already mentioned this, but let me put it down in the field. Right. So you have the PDT, right? And what does it say? So it says let us take like PT be the minimal polynomial of T. Of T. Okay. Since I've said matrices here, let me change T to of A, where A is a fixed D by D matrix. So I fix a D by D matrix, right? And I want to say that take this PT, right? And then this PT will decompose as T minus lambda 1 to the R1. Here I'm using that K is algebraically closed. T minus lambda K to the RK, with lambda 1, lambda K being distinct. Being distinct. And R1, RK bigger than or equal to 1. Okay. Then what does the primary decomposition theorem tell us? So the kernel of PT, or PA, right? This is the whole of V, or this is equal to, you can write R to the D, sorry, not R to the D, K to the D. This is a D by D matrix, and I'm thinking of V as KD. Right. Okay. I hope this is all right. I'm thinking of this matrix as acting on KD. This is, I'm thinking of it as D cross 1 row matrices. Okay, kernel of PA is by, since this is the minimal polynomial, P of A is 0. And therefore, the kernel of the 0 map is the whole of V, that is whole of K. Okay, that is equal to kernel of this A minus lambda 1, I, of course, to the R1, direct sum, kernel of lambda A minus lambda 2, sorry, minus lambda K to the RK. Okay, this is what the primary decomposition theorem tells us. Okay, and if I look at this here, so A has only lambda 1 as eigenvalue here. So these are invariant subspaces. see, these are invariant for A, meaning if I take, this is a subspace, and if I take an element, take a vector in this subspace and act A on it, that will continue to remain in this subspace, right? Because this operator commutes with the operator A. Okay, this is a polynomial in A. Therefore, that operator commutes with A. Therefore, if I take a V that belongs to the kernel of this, act A on it, then the resulting vector, namely A times that vector. So let's say that, let's call that vector V. And if I act A on it, I get A times V. That also will be in this kernel. Okay, these are invariant for A. So you can think of these as, so you can think of, when I restrict A to this, when now I think of A as a linear operator, this subspace, when I can restrict A to this subspace. Okay, and here I can, the point here is that I can always find, can you so here is the point. Let's call it Vi. Let's put Vi is equal to kernel of A minus lambda I to the Ri. Okay. Then Vi is invariant for A, is A invariant. And there is the point, we can choose a basis for. So what I want to do is choose a basis in which this operator A looks as simple as possible. So, claim is that there exists an eigenvector with eigenvalue lambda I in Vi. How do I prove this? For A. Can somebody tell me how to prove this? In this subspace, I'm claiming that there exists an eigenvector with eigenvalue lambda I. How would you prove that? By the way, so let's also say, so let me ask you another question. Why are the Vi not equal? Why shouldn't this be 0? What happens if this were 0? So let's take an example. Right? So suppose my PT is T, just let's take a simple example, T minus 1 into T minus 2. Right? And I take V to be kernel of V1 to be kernel of T minus 1, V2 to be kernel of T minus 2. Okay, maybe I should put a capital T here, never mind. So T acts as A. T acts as the matrix A. Okay, so whether I write capital T, whether I write small t, or whether I write A, they're all the same thing. Okay, and so we have V is equal to V1 direct sum V2. Why is V1 not 0? What if V1 were equal to 0? What would happen?
T minus 1 be minimal polynomial.
Ah, right. So if this were 0, then notice that kernel of T minus 2 would be everything, right? If this were 0, V would be, if V1 were 0, implies V is equal to V2, right? Which means, but T minus 2 kills V2, which means T minus 2 V is 0. But that's a contradiction, because minimal polynomial is T minus 1 into T minus 2. It's not T minus 2. Okay, so none of these can be 0, because if that were, if for example, if this is 0, then T minus, so say this one, A minus lambda 1 I to the R1 is 0, this kernel is 0, then if you leave this out, the rest of it would be would be satisfied by A. And that would, the minimal polynomial, I mean, then, but that cannot be, because the minimal polynomial must divide that thing. And if this has a T minus lambda 1 to the R1, something that doesn't have this factor cannot be divisible by that. Okay, so this is answer. Thank you, Anand. Now, can you please answer this one too?
So
Why
you
does
take A minus lambda I power Ri minus 1 at V.
Okay. So say that again. Very good.
A minus lambda I.
A minus lambda I.
Power Ri minus 1.
Okay.
At V.
Okay, I take this and then do what?
Because this Vi contains a non-zero vector, so we can take that non-zero vector.
Okay, I take
V
non-zero, which is what we have just shown in Vi. Okay, I do this and then.
Therefore, acting at this V, therefore this is the eigenvector of A minus lambda I.
Why is this non-zero? If in order to be true, your claim A minus lambda I kills this, but why is this non-zero?
Because we take this algebraic multiplicity is Ri, right? So
what? You just took some V. Just took some V.
This is the minimum.
Yeah, but you just said V is in. I took some arbitrary vector V in Vi that is non-zero. Then this could very well be 0, right? But you are on the right track. You're on the right track. You just have to say that, an arbitrary non-zero vector in Vi is not good enough. But you have to say that.
Maybe you can take the generalized eigenvector corresponding to this lambda.
No. Just no. What do you mean by that? Every element here is a generalized eigenvector for lambda. So if you choose just any V, that will be satisfied by the A minus lambda I to the power Ri will kill it. So the thing is, you choose a vector V such that, see, you can be more careful in your choice. Say, don't just choose a non-zero vector in Vi. Okay, the claim is there exists a vector V in Vi such that A minus lambda I to the Ri minus 1 on V is non-zero. Right? Because if A minus lambda I to the Ri minus 1, V were equal to 0 for all V in Vi, then
we get T minus lambda is power R minus a minimal polynomial. It's a factor of
exactly. Very good. Is that clear now?
yes.
Okay. Then PT would have been equal to T minus, or rather PT would divide. Okay. T minus lambda 1 to the power, or lambda Ri to the power R minus 1, and the rest. Right? So I could have, instead of T minus lambda 1, lambda I to the power Ri, I could have taken T minus lambda I to the power Ri minus 1. Okay, and that would be a contradiction, right? Is that okay, Annamalai?
Yes.
Okay, good. So now that is clear. Now I take this V, right? So I take this. So I choose such a V, meaning V such a, this is non-zero. Now put W is equal to this thing, A minus lambda I to the Ri minus 1 V, right? Then W is non-zero, and W A minus lambda I, W is equal to 0, because A minus lambda I W is, I substitute for W from here, it is A minus lambda I power R, power into A minus lambda I to the power Ri minus 1 V, and therefore this is A minus lambda I to the power Ri V, but that is equal to 0. Is that all right? Okay. Now that proves the claim. Now, what did you want to prove? So this QED for the claim. Okay, but what we want to claim is this. See this. We can choose a basis for Vi such that the matrix of A restricted to Vi. Remember, Vi is an invariant subspace, so this makes sense. The matrix of A restricted to AI, meaning the matrix of, what this means is of the linear transformation, A restricted to Vi. Okay, is of the form lambda I, and some star here and 0. So this is upper triangular with lambda I under that. Okay, let me do this. So see, the easiest way to prove such things is to think of the quotient space. So what you do is you choose an eigenvector for eigenvalue lambda I. You choose that to be the first vector. When you apply A on it, what do you get? It's an eigenvector of eigenvalue lambda I. So A V1, you will get to be lambda I V1. So when I write the matrix, I'll get V1 is equal to lambda I times V1. So this will become lambda I 0, 0, 0, 0. If I complete V1 to a basis, then the expression for lambda I V1 in terms of V1, V2, V3, etc. is precisely lambda I V1 plus 0 V2 plus 0 V3, etc. So this first column will become lambda. Then what you do is you observe that the space spanned by V1 is, so you go modulo that. Right? You go modulo that, and by the same argument, so you have an eigenvector in that quotient space. Right? So choose an eigenvector for eigenvalue lambda I in that quotient space. Call that V2, right? Or rather, its lift back in Vi to be V2. Then what happens is you see when you take this V2, it is 0 in the quotient space. When I act A times V2, it gives me lambda I V2 bar. That is A V2 bar is equal to lambda I V2 bar. So what this V2 bar means that it is it could be some up to a factor of up to an addition of a factor of something in V1, right? So what this means is A V2 is equal to lambda I V2 plus something V1. So this will become, like, this star represents that, right? And then A V3 similarly. So V3 is, again, you go modulo V1 and V2, the subspace spanned by V1 and V2. Pick V3 to be or V3 bar to be a eigenvector in that space. V3 can be a lift of that in Vi, and then you will get lambda I V3 plus something plus some star V2 plus some star V1, because this is in the space that you've gone modulo, etc. And if you do that, you will get this matrix. Okay. Anyway, okay. So let's continue this discussion next time. We are out of time today. Thank you for your attention. I will distribute. I will send it to Netco, the tutorial sheet on primary decomposition theorem, and I hope you will try those problems, and we will discuss them on Saturday. Good sign?
Yes, sir.
Yes, sir. Yes, sir.
Thursday, no session.
Hello?
Yes, sir.
Yes, sir. Coming Thursday, no session, sir. Saturday, only the next session.
Am I audible?
Yes, sir.
Yes, sir.
Hello?
Yes, sir. Yeah.
Okay.
For audible, sir.
Audible, sir, audible.
Audible, sir.
Okay, very good. So Saturday, right? We are continuing. Thursday, there is no.
Yes, sir.
Yes, sir. You are correct, sir.
Okay. Let's continue on Saturday. So I'll send out this problem tutorial sheet. I may add more problems, but